All right, let's dive into one of the weirdest, most fascinating ideas in all of physics, neutrino oscillations. We're going to break down how a tiny, fundamental particle can literally have an identity crisis mid-flight, and we'll be using some great research from the Indian Institute of Science in Bangalore to guide us. I mean, just think about that question for a second. How can something fundamental, something that's supposed to be a basic building block of the universe, just change what it is? It sounds like it breaks all the rules. But in the quantum world, the rules are, well, they're a lot stranger than you'd think. And the answer to this one question completely flipped our understanding of physics on its head. So let's start with the particle at the center of this whole mystery, the neutrino. What is it? Well, it's a fundamental particle, which just means it isn't made of anything smaller. It's got no electric charge, and it barely interacts with, well, anything. They're so ghostly that right now, literally trillions of them are zipping through your body without you ever feeling a thing. And get this, they come in 3 different types, or as physicists like to call them, flavors. You've got the electron neutrino, the muon neutrino, and the tau neutrino. Now, for the longest time, the thinking was simple. A neutrino is born with a certain flavor, and it stays that way forever. An electron neutrino is always an electron neutrino. Simple enough, right? Well, it turns out reality had a major plot twist in store. And here's where things get really interesting. The standard model of particle physics, our absolute best rulebook for how the universe works, was built on the idea that neutrinos have 0 mass. And if they're massless, their flavor is supposed to be locked in for good. But then, experiments started seeing the impossible. Neutrinos were changing flavors. A neutrino born as an electron flavor in the sun might show up here on Earth as a muon flavor. This wasn't just a small correction. This observation completely shattered the old belief. And this is the absolute kicker. Physicists realized that these 2 ideas are totally connected. The only way a neutrino could possibly change its flavor is if it has mass. If it were truly massless, it couldn't change, period. So finding out that they oscillate wasn't just a cool fact. It was a revolution. It proved the standard model had a huge piece of the puzzle wrong. So how in the world does a particle just switch teams? How is that even possible? Well, the answer comes from one of the most famously bizarre, mind-bending principles of quantum mechanics. It's a little thing called superposition. See, in our big, everyday world, a light switch is either on or it's off. It can't be both. But down in the quantum realm, a particle can be in a mix of different states all at once. It's not one or the other, it's a weird, fuzzy blend of all the possibilities. And our source material uses this perfect analogy for it. Think of a neutrino not as a pure shot of something, but as a quantum cocktail. It's a specific, precise mixture of other, more fundamental ingredients. And this idea is the key to this whole thing. Okay, so here's how this quantum magic trick works, step by step. First, when we create, say, an electron neutrino, what we've really created is a specific cocktail recipe, a precise mix of 3 underlying mass states. Now, these mass states are what actually travel through space. But here's the trick. Because they have slightly different masses, their quantum waves get out of sync as they travel. By the time we go to detect that particle way down the line, the recipe for the cocktail has changed. And that new mix might just be what we recognize as a muon neutrino. Its identity has literally shifted while it was flying through space. So what determines how likely it is to change? Well, it all boils down to 3 main things. First, that original cocktail recipe, the specific quantum mix it started with. Second, the difference in the square of the masses between those underlying states. And third, a simple ratio, how far it's traveled divided by its energy. And because the probability of seeing one flavor versus another goes up, and down, just like a wave as the particle travels, that's exactly why we call this phenomenon oscillation. The neutrino is literally oscillating between different identities. Wild, right? And if that wasn't weird enough, there's a bonus twist. The trip itself can change the odds. If a neutrino has to travel through a bunch of dense matter, like, say, the core of the sun or right through the Earth, that can actually change the probability of it oscillating, especially for the electron neutrinos. It's called the MSW effect, and it just goes to show that even the environment plays a role in this quantum drama. Now, I know what you're thinking. This all sounds like some crazy made-up theory. But how do we know it's actually real? We know because of some absolutely brilliant experiments that managed to catch these little ghost particles in the act of changing their minds. The proof really came from 2 major sources out there in the cosmos.
First, scientists built these huge detectors to study neutrinos streaming from the sun, and they found a huge problem. About 2/3 of the electron neutrinos they expected to see were just missing. They hadn't vanished. They had oscillated into other flavors on their long journey to Earth. This gave us our first clue about the mass difference. Then, other experiments looked at neutrinos created when cosmic rays smash into our atmosphere. They found a different pattern of oscillation, which pointed to a second, totally different mass difference.
And finding two separate mass differences? That was the smoking gun. Mathematically, there's just no way to get two different results unless you have at least three different mass states, our little V1, V2, and V3 making up the cocktail. The real-world data fit the wacky theory perfectly. Okay, so a super tiny particle has a weird identity crisis. Why should anyone care? Well, it turns out this isn't just some quirky little detail. This has massive consequences for our understanding of the entire universe. You see, the fact that neutrinos have mass isn't just a footnote you add to the standard model. It's proof that the model itself is incomplete. This discovery was the first major crack in our most successful theory of physics, and that crack is a doorway. It's pointing the way to something deeper, something more complete. This is the frontier of physics. And you have to remember, they may be almost massless, but there are an unbelievable number of them. Just let this number sink in. About 100 trillion neutrinos, mostly from the sun, are passing through your body every single second. They are, without a doubt, the most abundant particles of matter in the entire universe. And that's why their tiny, tiny bit of mass matters so much. When you take a very small mass and multiply it by a ridiculously huge number, you actually get a significant amount of mass for the universe as a whole. In fact, that collective mass might be a key ingredient in explaining how gravity had enough oomph to pull matter together and form the very first galaxies and the massive cosmic structures we see today. But you know how it goes in science. Finding an answer to one huge question doesn't end the story. It just blows the doors open to a whole new set of even bigger, deeper mysteries. For starters, even though we know the differences between the masses, we still have no idea what the actual mass of any single neutrino is. We don't know how heavy the lightest one is. It's kind of like knowing the height difference between three people, but having no clue how tall any of them actually are. And then there's this tantalizing question. Are there only three flavors? Some strange results in a few experiments have hinted that there might be a fourth type of neutrino out there, one they call a sterile neutrino. It would be even more ghostly than the others, and finding it would once again change everything. And maybe the biggest, most profound question of all is this. Is a neutrino its own antiparticle? See, most particles have an evil twin made of antimatter, but it's possible neutrinos are unique. If they are their own antiparticle, it could help us solve one of the greatest puzzles in all of cosmology. Why are universes made of matter and not antimatter? So what started as a simple counting problem, just some missing particles, unraveled into this incredible story. A tiny particle's identity crisis showed us a major crack in our best theory of physics. It revealed the neutrino's hidden role in shaping the cosmos, and it left us with this amazing roadmap of new mysteries that physicists are racing to solve as we speak. The story of this ghost particle is far from over.